Right, the next speaker is Dumitrescu, and he'll tell us about symmetry breaking from monopoles in 3D QED.
All right. Thanks very much, Sylvia, and thanks very much to the organizers for inviting me to speak and for putting together such a wonderful conference. So I'm going to tell you about some recent results about three-dimensional QED, which has kind of long been an interesting theory for many reasons, and among other top reasons is that it's sort of a simpler cousin of interesting dynamics in 3D or 4D QCD. And the results I'll tell you about appeared in two recent papers that appeared within the last 6 weeks or so. One is by Shai Chester and Zohar Komargotsky, and one is by myself and Pierluigi Nero and Ryan Thorngren, who were at that time all at UCLA. Now Pierluigi is a postdoc at CISA. So I will obviously tell you about my perspective on this problem, but if I get to the end of my presentation, I'll also mention some of Shai and Zohar's results. All right. And after we put out our papers, we decided that there were also some interesting kind of open questions that we still wanted to think about, so we teamed up, and now there's some work in progress with all of these people that I might also mention. Okay, so I'm going to talk about QED in 3 dimensions. What do I mean by that? I mean that I will discuss U1 gauge theory. There will not be a Chern-Simons term, so I'll set the Chern-Simons level to 0, and then I'll add NF Dirac fermions. Here I'm doing Dirac fermions in 2 dimensions, so alpha is a 2-component index and I is a flavor index. And if I insist on setting the Chern-Simons level to 0, then NF has to be even due to the parity anomaly. So I'm going to discuss this theory with an even number of Dirac fermions of U1 charge 1. These all have charge 1 under the dynamical U1 gauge field. And the Lagrangian is just the standard QED Lagrangian. Quickly write it. So I here is a flavor index. And here's the gauge field, and F is the field strength of the dynamical U1 gauge field. You see here that because the only charged matter fields are fermions of charge 1, fermion number is actually gauged in this theory. And therefore, it's actually a bosonic theory in the sense that all local operators will be bosonic, and you do not need the spin structure to think about this theory. That will be important when we discuss things like anomalies. All right. So, in a kind of spirit similar to the one that Ofer discussed in his talk on Friday, I'm going to consider this theory as a function of NF. And it's a classic result that if you consider the theory at very large NF, somewhere here, it's weakly coupled, can be solved in a 1 over NF expansion, and the effective expansion parameter is 1 over NF. And what you find here is a weakly coupled CFT. A weakly coupled CFT where all the global symmetries of the Lagrangian are unbounded. So it's a CFT that preserves all of the symmetries. As you dial down NF in units of 2, in order to be consistent with my rules, the coupling, the effective coupling becomes stronger and stronger. So eventually, you don't know what's going to happen here, and you lose strict analytic control. And there's been a lot of research on what happens to these theories as a function of NF, analytic, numerical, and etc.
And weakly coupled CFT is it infrared or in UV?
In the infrared.
Is the infrared?
They're sort of Banks-Zaks-like, very short RG flows from the UV to the IR,
Okay.
and you can calculate in 1 over NF.
Okay.
All right. Now, the question that has been asked for a very long time is how low can you make NF and still have a CFT? Or in other words, is there some value of NF at which this theory stops being a CFT? That's the question about the end of the conformal window. And as I said, there's been lots of work on that, but a recent kind of new addition to the discussion has been the constraints coming from the conformal bootstrap. Because whenever such a CFT exists, it must satisfy the constraints from Bootstrap. And if one takes the recent Bootstrap results seriously, then they amount to the statement that the theories with an f down to 4 appear to be consistent with a CFT, with unbroken symmetries, but this does not appear to be the case for this lowest value of an f, which is 2. Remember, nf equals 2 is exactly the same number of fermions that you have in 4D QED. Nf equals 0 is just free Maxwell, we won't discuss it. All right. So the starting point for my discussion is the assumption that this theory with 2 flavors does not flow to a CFT. And if it does not flow to a CFT, we should ask what does it do? And it's natural, and in fact inevitable, to consider scenarios with spontaneous symmetry breaking, and that's going to be the subject of the talk. So let's, for the rest of the talk, we're just going to focus on this case here with n f equals to 2. We're done talking about all the higher values of n f. So let's discuss, since we want to talk about symmetries, let's discuss what are the symmetries of the theory with n f equals to 2. Well, there is an SU2 flavor symmetry that rotates the 2 Dirac fermions in a doublet representation of SU2. And then it turns out that there's also a U1 monopole magnetic symmetry. They're identified like that, so that the whole symmetry group is actually U2. And this is the zero form symmetry. This is the group of symmetries that act on gauge invariant local operators. So let me say a few words about what the gauge invariant local operators are. They're standard local operators constructed out of the fields, psi and f. So for example, one important operator that's charged under the SU2 symmetry is the fermion bilinear, the gauge invariant fermion bilinear in the triplet representation of SU2. That would also be the conventional symmetry breaking order parameter, and it'll make an appearance later. It turns out that all these like normal local operators are not actually charged under the center of SU2, so they transform under SO3 symmetry. But the theory famously also has monopole operators. This is an abelian gauge theory in 3 dimensions. And there's a U1 magnetic symmetry that acts on disorder operators that insert some number of units of Dirac flux into space-time. So we also have monopole operators that are charged under this. So if I make a monopole of charge Qm, then the integral of the gauge field over some sphere surrounding this point is 2 pi Qm. And in the presence of the fermions, these monopoles can also acquire quantum numbers under the SU2F symmetry. And
Do you mean that your U1 is actually compact?
so my U1 gauge group is compact.
Okay,
So I have monopole operators,
that's understandable.
but unlike in the discussion of confinement by Sasha, I'm not adding them to the Lagrangian. So U1 magnetic is actually a global symmetry of the theory that I'm considering, and then you can ask whether or not it's spontaneously broken.
Yeah.
So that's going to be what happens here.
So
But you
monopoles
can
are
have
heavy.
magnetic quarks. You can. Is it possible to gauge and to have magnetic interaction as well? No, I mean because your AMU, I mean it's not magnetic field, right? I mean not magnetic field. I mean gauge field.
Let's discuss this theory, and then at the end of the talk, if I have time, we'll discuss a variant of it.
Yeah.
The smallest possible monopole operator with charge 1 under this U1M is what I'll call script M I. It's actually a fundamental of this U2, so it has monopole number 1, and it's a doublet under the SU2. If you just think group theoretically, this U2 is like the standard model gauge group, and this has the quantum numbers of the standard model case. So if you want to figure out the group theory that's coming up, you can keep this analogy in mind. All right. So the main claim, which I'll try to justify a little bit to you, is that this theory with 2 quarks, right here, spontaneously breaks this symmetry. So the NF equals 2 theory, assuming it doesn't flow to a CFT, has spontaneous symmetry breaking, which is triggered by the expectation value of this monopole operator. Okay. In the past, there was intense discussion about all sorts of interesting things that could happen if the NF equals 2 theory did flow to a CFT, and those are interesting, but I emphasize that this is not what I'm discussing here. I'm considering the alternative, which seems to be implied by Bootstrap. All right, so what happens when Mi gets a BEV? Well, remember, because the quantum numbers of a U2 fundamental, that means it spontaneously breaks U2 to some unbroken U1 subgroup. Let me call it U1 unbroken. The standard modulus would be electromagnetism, but here it's a global symmetry. And because U2 is broken to U1, there are 3 Goldstone bosons. The 3 Goldstone bosons sit in the coset of U2 by U1, and this coset is actually, I'll write it here.
So the fermion bilinears have 0 BEV?
We'll get to the fermion bilinears. They actually have non-zero BEV, but in a special way. Okay, so the coset is S3, which is just the usual quotient. This S3 tilde is just to indicate that this S3 doesn't have its full maximal O4 isometry. It only has the U2 isometry that's actually there in the theory. So that means that the S3 is, if you think of it as a Hopf vibration, which I'll describe in a second, has the Hopf fiber squished a little bit relative to the base. Very good. So let me describe the Hopf vibration, and then I can also answer Silviu's question and tell you what happens to the fermion bilinear order parameter. Okay, so a nice way of describing this S3 is via the Hopf vibration of an S1 over a CP1 base. And the Hopf map from S3 to CP1 is just obtained by forming the following combination of monopoles. You take M dagger, M dagger sigma M. M dagger sigma M is not charged under the U1 magnetic, and it's a triplet under SU2F. And so this gadget, if you want, you can normalize it by the VEV, is a unit vector which describes the CP1 base, the vibration. Okay, so this is the usual Hopf vibration. And then let me draw you a picture of what the sigma model looks like. So I want to do a few things with it. I need a bunch of this. So if you take the CP1 base of the vibration, which is just an S2, right? Then different ends parameterize this sphere. So let's, for example, take the North Pole or the South Pole, where n is plus or minus z hat. Then at those 2 points, the Hopf fibers are basically circles over these points. The important thing is that because of the non-trivial vibration, the broken and unbroken symmetries at those points are different. Right? If you just knew about this triplet order parameter, this n being non-zero, you would say that SU2F is broken to its cartan, U1. But what happens here is that the monopoles fibered over the North Pole look something like this, where sigma is a compact boson that parameterizes the Hopf fiber here. And if you look at the monopoles fibered over the South Pole, their VEV looks something like this, with an e to the I sigma and the bottom component. So you have different linear combinations of this U1 cartan that preserves both the North Pole and the South Pole, and the U1 magnetic that multiplies the m's by a face. Right? So here you get the sum, and here you get the difference being spontaneously broken. So the number of Goldstone bosons is the same, but which symmetry is broken and unbroken is non-trivially fibered over the CP1 base. So that's just the statement of the vibration. All right, let me make a quick comment about anomaly matching. There's a lot I could say about it, but I want to say other things, so I'll say this quickly. The UV theory, remember, had a U2 symmetry, and in fact, it also has had other symmetries that I didn't mention, including time reversal. And there's a mixed anomaly between time reversal and U2, which is of parity type. So it's characterized by a 4-dimensional theta angle with value pi multiplying this instanton density of U2. It multiplies C2 of U2, which is some combination of the SU2 and U1 magnetic instanton densities. And time reversal alone restricts theta to either 0 or pi, and the fact that it's pi, it's non-trivial, means that there is such an anomaly. This is basically a version of the standard parity anomaly. And in the S3 sigma model, it's matched by adding a theta angle for that sigma model, right? S3 is 3-dimensional, so it has non-trivial H3. Therefore, you can add a theta angle in 3 dimensions that's proportional to the volume form of the sigma model. And if you dial the theta angle there to be exactly pi, then you match this anomaly, right? So the statement that you get an S3 sigma model is kind of enriched by the fact that you should also add a 3D theta term with theta equals pi for the sigma model field. So here I'm using F to denote the map from space-time to this S3. So this is what we would call a standard theta angle for a sigma model in 3 dimensions. It's a 3-form, gauge invariant 3-form. All right. Any questions?
Could I ask a question? You mentioned that your monopoles are non-dynamical, right?
Mm-hmm.
Which I can interpret that they're very heavy.
No, they're infinitely heavy.
Huh?
They're
Or
infinitely heavy.
Then how an infinitely heavy field can develop an expectation value, which is non-vanishing? If it has an infinitely large mass term, it won't condense.
In terms of the compact scalar sigma, you see that the monopole operator is literally e to the I sigma. Sigma is just a Goldstone boson, it's just a weakly coupled compact scalar. So if you have such a compact scalar and you compute the VEV of e to the I sigma, it's non-zero. This is a statement about.
But why it would be very heavy then? No,
The
sigma is
Goldstone
heavy.
boson is massless.
No, but isn't it true that effectively you write this term m squared times this m dagger m in effective Lagrangian, which makes them infinitely heavy, right?
I'm not adding monopoles to the Lagrangian. I'm just
fine tune. You
just fine tune the
lattice not to have monopoles. It's fine.
There are no dynamical monopoles, but it is a legitimate operator that you
In
can,
that theory.
in the theory, it's
Right.
just checking its
It's
value.
VEV.
External operator.
In fact,
External.
Yeah. all right, let me answer Sylvia's question and talk about what happens to the fermion bilinear. All right, so let me do it here. So the fermion bilinear is in principle another different SU2 triplet, and you could ask whether it's 0, you could ask whether it's non-zero, and if it's non-zero, you could ask whether it breaks the symmetry further or it's aligned with the M's. And the thing that we show is that this thing is exactly aligned with M via the Hopf method. So in other words, this thing is non-zero, so you can show that this is proportional to this with a non-zero coefficient. And that means that this fermion bilinear, which as I said is the standard order parameter for chiral SU2 breaking, is definitely non-zero, but it's aligned with the monopoles. Right? I already said that the monopoles give you a map into triplets via the Hopf map. And this order parameter is turned on in a way that's exactly aligned with that triplet. So when you search for signatures of this, one should search for both monopole valves and triplet valves at the same time. And in fact, if those triplets were misaligned, it would break the symmetry further and generate more Goldstone bosons, which does not happen. I should also say that most discussions of symmetry breaking in the literature have focused on this order parameter. And depending on how seriously you take the statements, if you only condense this order parameter, you should only see the CP1 base of the Hopf vibration. You should not see the fibers. So you should only have 2 Goldstone bosons. But then sometimes people add the massless photon in by hand. And the massless photon is just the usual dual, the usual, abelian dual of this compact sigma field. So roughly speaking, if you add the photon back in, you're discussing a variant of this scenario, and here we have a precise version of it.
But your M field is external and psi are dynamical, right? So it's a normal condensation of psi, right?
Mm-hmm. That's right. So in order to give you a flavor for how we arrive at these conclusions, I need to actually perturb the massless theory. So far I've just discussed symmetry breaking in the massless theory. Now I'm going to turn on masses, and there are different masses I can add. And roughly speaking, the 2 papers that appear differed in the kind of masses that they added. And the mass that I'm going to add is the mass that's proportional to this triplet. Okay, so I can perturb the massless theory by adding to the Lagrangian this. And then using SU2, I might as well take it to be aligned with the z-axis. Right, so let me add a mass perturbation, which is literally just sigma z. So a positive mass for one of the fermions and a negative mass for the other one. That has all sorts of advantages, including preserving the positivity of the measure that is, for example, important in the Vafa-Whitney theorem. So this perturbation is consistent with the Vafa-Whitney theorem. What happens when you add this mass? Well, when you add this mass, you explicitly break the SU2 to the U1 cartan. It is aligned in the z direction. So you pin the CP1 base to the north and the south pole. You pin it to these points. And in fact, you can show that it's aligned with M. So when M is bigger than 0, you're pinned to the north pole. When M is less than 0, you're pinned to the south pole. That way you can select every point on the CP1 base by dialing this M. But the sigma field, the sigma Goldstone boson, is not lifted by adding this mass, right? This is the monopole field. And so what you end up with at very small m is a phase in which there's just one Goldstone boson, which is the sigma. Here it's the sigma field corresponding to this monopole operator condensing, and here it's the sigma field corresponding to this monopole operator condensing. So you end up in what I would call the Coulomb phase, the single Goldstone boson for different linear combinations of U1F and U1 magnetic. And if you wish, you can dualize that sigma Goldstone boson and express it in terms of free Maxwell theory. So this little perturbation analysis that I just went over for you is really only valid for very small m's, right? Because I did it by perturbing the sigma model by a little bit, the way we do it for small quark masses in QCD. But in fact, this phase persists exactly like that for all values of m, and it's really easy to see at large m. So now let's do the analysis at very large m. At very large m, I can integrate out the fermions. One of them will have a positive sign, one of them will have a negative sign, so it will not generate a Chern-Simons term. And the low energy effective action will be kind of an Euler-Heisenberg type effective Lagrangian, which is basically free Maxwell plus higher derivative corrections. So let's take m to be huge compared to E squared, which is the strong coupling scale. Then at low energies, I just get free Maxwell plus higher derivative corrections that I won't write. And then it turns out that I get two interesting Chern-Simons terms. I get two interesting Chern-Simons terms if I remember that I have two global symmetries that are unbroken when I turn on this mass. I have the U1 cartan of the SU2, and I have the U1 magnetic. And those are unbroken by this mass term. So when you activate background fields for those two U1s, it turns out that there is an interesting Chern-Simons term for those background fields with the dynamical gauge field. And it's easy to compute using the quantum numbers of the fermions the Chern-Simons term involving AF and the dynamical gauge field depend on the sign of the mass. And then there's another Chern-Simons term which doesn't depend on the sign of the mass, which couples the U1 magnetic background field to dA. Thank you. This just tells you that the monopoles of this Maxwell theory have, the minimum monopoles of this Maxwell theory have magnetic charge 1. That's what you would expect. This tells you that for positive M, the monopoles have U1 flavor charge 1, exactly as these monopoles here did. And for M less than 0, very large, it tells you that they have negative U1F charge. So they are exactly these monopoles that we had in the small m phase. You see that the large m phase and the small m phase are actually continuously connected. The symmetry breaking patterns are the same. You just have a weakly coupled photon, or if you wish, a weakly coupled sigma Goldstone boson for all non-zero values of n. And we can actually prove that nothing interesting can happen in between using a variant of the Vafa-Witten theorem, which basically says that the moment I turn on this mass, then all the charge degrees of freedom in the theory disappear exponentially at long distances, so that you're only left with free abelian gauge theory. So I've argued that this is natural based on the large n and the small m regimes, but in fact we can prove that there's an entire continuously connected Coulomb phase for all non-zero m, where the symmetry breaking looks like that. So when you know that, it's kind of intuitively clear that when you take m back to 0 and you study symmetry breaking in the massless theory, you'll basically reassemble this picture from different angular approaches. So that's not quite the proof, and there's a couple of scenarios that you have to rule out in order to deduce the main claim that I made about symmetry breaking, but you can rule out all possible alternatives by appealing to this finite m deformation of the massless theory. So once you know that the finite m theory is just free Maxwell with these Chern-Simons terms, all alternatives are ruled out. Okay, and in the last 5 minutes or so, let me kind of give you a dual perspective on this problem, which is the one considered in the paper by Shah and Zohar, where instead of turning on this triplet mass, we turn on the same mass that Ofer studied in his talk on QCD on Friday. This is the mass that preserves the SU2F flavor symmetry, but breaks time reversal. So if you do that instead, study the T-breaking mass, then the Vafa-Witten theorem no longer holds. Here's the massless point, which I said was my squashed S3 sigma model with a theta angle. At very large positive and negative mass, you integrate out the fermions and you get, in general, a Chern-Simons theory, but here it's actually invertible. It's just some SPT. And the question is, how do you fill in this phase diagram as a function of this M? And what they proposed is that the S3 sigma model phase here and here continuously matches on to second order phase transitions that are described by O4 CFTs. So they glued together the phase diagram of two O4 models. The symmetry breaking phase here is just the symmetry breaking phase of the O4 model, and then the phase out here is the one that you would normally think of as the trivial phase of the O4 model, and there was an interesting discussion that they gave about how this is consistent with the presence and absence of these SPTs. All right. So, since I have 1 minute left, let me maybe summarize, make a small comment about how one could try to look for this scenario on a lattice. So I argued that in the theory with gauge group U1, where the monopoles are local operators, the monopoles get a VEV and the fermion bilinear gets an aligned VEV, and there are 3 Goldstone bosons. So if one is able to simulate this theory, one can actually look for that. For example, the fact that there are 3 Goldstone bosons should affect very crude quantities like the free energy. But there's an interesting variant of the theory where you take the gauge group to be, instead of U1, you can take it to be R. And that is a little bit easier to simulate on the lattice for various technical reasons. And the usual lore, at least for a long time, has been that the theory with gauge group R doesn't have monopole operators. And it's true that the monopole operators in the R gauge theory are not local, but it turns out that the R version of the gauge theory has what is sometimes called a Z1 form symmetry. And therefore, the monopoles that I discussed as local operators still exist in this theory. They're just attached to some very benign topological lines. And one way of obtaining this R version of the theory from the U1 version is to gauge the U1 magnetic symmetry, but to do it in a way that doesn't add a photon. So sometimes people call this flat gauge. You just path integrate over flat connections of U1 magnetic, not over all possible gauge configurations.
Like direct monopoles.
So direct monopole.
Direct monopoles, right?
Exactly.
Yeah, that's right. So this is literally the Dirac string.
Yeah.
And so this version of the theory, for example, you could consider the following kind of string-like order parameter. And that thing should have a VEV at large distances, which exactly captures the VEV of the local monopole operator in the U1 version of the theory. So I think it would be interesting to look for that in the R version of the theory, because it can be simulated on the lattice somewhat more straightforwardly than the compact version. All right, thanks.
I just want to make a remark. On all gauge theories, on R3 cross S1, where there is some discrete chiral symmetry or continuous chiral symmetry, if you construct small S1 limits by using adiabatic continuity, what happens is very similar to this scenario there. You know, fermion bilinear gets a VEV because it aligns with the monopole operator. So the first monopole operator, there of course monopoles are condensing. Monopole operators are condensing, and fermion bilinear gets a VEV because of that.
But one thing I want to say is that in this theory, the monopole operator is a standard local operator.
Same
Right.
there. Same there. And
Well,
the other,
Depends
at
on the
least to
examples.
my mind, relatively
It's a well-defined operator already in the UZ. Okay?
sure.
That's not the case if you're studying some 4D gauge theory on a circle.
No, on S1, yeah, it is at distances larger than theory abelianized as Yuan goes, starting at that scale.
Right.
But I want to also bring one other analogy. Actually, you can devise QCD with fundamentals, such that all the number Goldstone bosons are actually realization of the dual photons. This is something very surprising to me. And this is the same phenomenon as it is there in this case. One wonders, if there is a deeper reason for that.
Yeah, kind of making the dual photon on a billion.
Right.
So very simple enough.
Yes. Good questions.
Any other questions?
Thanks.